All right, guys, let's go ahead and get started. All right, so today, gonna be honest, I don't have a whole lot planned. I think we'll be able to finish out the period, but we'll see. But I'm really wanting to just a couple little tidbits I want to finish up in chapter 20, and then I want to explore synthesis and do some practice there because we have kind of a new angle on things now we can take in synthesis. All right. So, all right. Last time we met, which was a while ago because of Easter, I think we had talked about organometallics, right, and the various types of organometallic reactions that we can get with carboxylic acids and their derivatives, aldehydes, and ketones. All right, there's one more type of organometallic reaction I want to show you. That's reaction of an organometallic with what we call an alpha beta unsaturated carbonyl compound. It's kind of a mouthful. Okay. All right, alpha beta unsaturated carbonyl compound. Sounds kind of fancy schmancy. In reality, it's something that's just going to contain this group, right? You're going to have a carbonyl group, and then directly adjacent to that carbonyl group, you're going to have an alkene. Sometimes called an acrylic group, too. You may have heard the term acrylic before. All right. And as far as what's over here, you can have several different things. You can have acidic forms of these, so you can have like carboxylic acids. Over here, you could have aldehydes, ketones. You could have, esters, acid chlorides. Well, we're actually just going to focus on aldehydes and ketones right now. So I'll just show you the ketone. All right. So, hold on one second. Something up real quick on my online book. Oh, I just realized I'm in the wrong chapter here. Great. I couldn't find what I was looking for. Give me a second. This is why I should probably start carrying a real book to class. Okay, so there's a couple of different reactions you can have here with organometallics. They're called 1,2 and 1,4 additions. And that might sound familiar, right? We did 1,2 and 1,4 additions with conjugated diamonds, right? You can also do 1,2 and 1,4 additions with these guys. Right? It's really simple to remember. When you do a 1,2 addition, you're going to take one of these, and you're going to react it with a strong organometallic. So let's say we wanted a methyl group here. We could do something like CH3Li. Followed up with H2O, just like we've been doing. All right? Whenever you have a strong organometallic, you get 1,2 addition. That means we're going to get our traditional attack on your carbonyl carbon, right? So this one should seem pretty natural based off of all the stuff that we've done already. It's just the same, basically the same as usual, right? You just happen to have an extra carbon-carbon double bond just sticking out there. It'll create a negative O. And negative O. Rattle proton. And give you a final product. And in this particular case, we have a racemate since we ended up creating a new stereogenesis. Okay, so this is what happens with strong organometallics. Either organolithiums or Grignard reagents. Okay, that make sense? Any questions? All right. Now, you can also get something called a 1,4 addition. So we're going to take the same molecule here. And instead of adding a strong organometallic, we're going to add a weak one. Let's say we added, I don't know, add an organocuprate. We're going to add an organocuprate that has 2 ethyl groups on it. And we're going to follow it up with H2O. All right. So what tends to happen here is instead of getting attacked on the carbonyl carbon, you still have the ethyl group coming off and attacking something, right? But instead of attacking here, it attacks your carbon-carbon double bond instead. Why, you may ask, and not the carbonyl carbon? I don't know. But we know it doesn't, so that's the guidelines we use, right? Yeah, you're always going to attack the carbon-carbon double bond. And you're going to do so in a manner that attacks the carbon furthest away from your carbonyl. So you're not going to attack this carbon. You're going to attack the one that's further away, right? That means these electrons go over to that carbon. You have that. Carbonyl carbon remains unscathed. Nothing happens to it. And then lastly, this will grab a proton, and you'll get your final product. Which in this case happens to be a ketone. Okay. Any questions? This is actually super easy. I mean, alpha beta unsaturated carbonyl compounds, it sounds all kind of complicated, but it's really not. There's only 2 things that can happen. We don't tend to get resonance products or anything from this. Just have to remember, strong organometallic attacks the carbonyl. Your organocuprates, weak, are going to attack your alkene. Okay. Any questions? All right. All right, there's a couple of other interesting little redox reactions I want to mention here that kind of fell outside the realm of the major categories. They're not hydride reductions. They're not going to involve organometallics, but there's still a couple of important reactions that involve carbonyl compounds, specifically aldehydes and ketones. I think we've actually mentioned this before in a previous chapter, but I'm going to revisit it just so you guys have it fresh. All right, I know we talked about catalytic hydrogenation, right? Reach back into the depths of your memory banks. What do you remember about catalytic hydrogenation? All right, like go up to your face, look at you straight in the eye, tell me everything you know about catalytic hydrogenation. What would you say? Probably don't want to know. We used this in a previous chapter. What kind of materials do you think you need for catalytic hydrogenation? Dear God, tell me you can get one of them. What's that? You do need a catalyst. It's not the one I was expecting to hear, but yes. Yes, absolutely. Very specific type of catalyst. What types of catalysts work for this? What's that? Lindlar works. Yep. If you want to do a mild hydrogenation. If you want a stronger one, platinum, palladium, nickel, right? Yeah. What's the other major ingredient we need?
H2 gas.
Need hydrogen. Gonna do a hydrogenation, you need hydrogen, right? So H2. And then what was the group that we looked at before that typically got hydrogenated? That one may be a little bit tougher for you to remember.
Alkene.
It was alkenes. Yeah, you guys remember doing something like this? You know, you could have, you know, an alkene group, right? H2, platinum. Each one of the carbons in the double bond gets an H. Does that ring a bell? Okay. Funny thing about this is that this will also work for aldehydes and ketones. It can also attack carbonyl groups as well. So I could do the same exact reaction on a ketone. And yeah, it would treat this carbonyl just like it would a carbon-carbon double bond. Each one of these atoms gets a hydrogen. So you can do catalytic hydrogenation of a ketone, and you see you get an alcohol. Specifically a secondary alcohol if you use a ketone. So on a primary alcohol, you can use an aldehyde. Right? Mechanism works exactly the same way. I'm not going to go over that again. It would basically suffice to say both the carbon and the oxygen get a hydrogen. All right. Here's a consideration. What if we had something like this? Put some palladium in there just to be different. What do you think would happen if we did that? Just one equivalent of H2. It can go after both of them, right? What do you think? Are we going to have a preferential group? Are we going to have a mixture? Who says it's going to prefer the carbonyl? have a good old fashioned vote. We have one person, two people. How about who prefers the alkene group? One person. Who says a mixture? We had literally 3 people vote that I saw. Unless he just like did, you know, this kind of thing. Yeah, we literally had 3 people. Wow. Problems with our democracy. There we go. All right. You'd actually get that. Hydrogenation prefers to go after carbon-carbon double bonds. So if it's got a choice, it'll attack that. It'll attack, excuse me, this right here. Now, if you added 2 equivalents, then it would attack both of them. Yep. So remember that. That's actually used quite a bit. You can definitely hydrogenate aldehyde and ketone carbonyls, but if you have a carbon-carbon double bond in there, it's definitely going to prefer to go after that. Okay. Any questions so far? All right. All right, and the last category of reactions I want to mention here, or last type of reaction, is oxidations. Specifically, oxidations of aldehydes. I'm going to put something up here from the redox chapter, something we've already gone over, but I want to sort of refresh you on it. Y'all remember we said if we wanted to oxidize an alcohol, a primary alcohol, there were a couple of different avenues we could go down. We could add a strong oxidizing agent, something chromium based, like, you know, CrO3 or Na2Cr2O7 or something like that. We can add a strong oxidizer. What did we say this oxidizes primary alcohols into? What type of functional group? Carboxylic acid, right. We call it strong because, hey, it jumps a level. We go from 1 bond to oxygen all the way to 3. We also said with primary alcohols, we could do a more gentle oxidation. Like we could just go from 1 bond to oxygen to 2 and form an aldehyde instead by adding a different type of oxidizing agent. Y'all remember what that was? PCC. Not PCP, that would be something entirely different. I've actually had people put that on exams before. Add a little angel dust to your alcohol. Good Lord, that sounds terrible. Don't ever do that. All right, anyway, that allows us to make an alcohol. Excuse me, an aldehyde, all right? So you see there's a couple of different levels of oxidation here, right? Well, one logical question that you might ask yourself would be, well, can I just take an aldehyde, an existing aldehyde, and go ahead and turn it into an acid? Yes, you can. Absolutely. There's multiple ways that you can do it. Probably the simplest and easiest way, we go from here to here, is just go back, take that strong oxidizing agent that you can add to primary alcohols, add it to an aldehyde instead. That'll get the job done. So chromium trioxide is used a lot, but again, you could use some of the other chromium-based compounds that we previously went over as well. All right, so it is possible to go directly from an aldehyde to an acid using the same methods. I want to show you another cool one though here. Let me find my reference page. There we go. Come on, I lost it. Christ. This is the bad part about having an online or a e-textbook. There we go. So let's say we add an aldehyde. Another way of doing this is to add Ag2O. Ag is silver, if you don't remember. That is silver oxide. In the presence of NH4OH, ammonium hydroxide. Basically what happens here is silver ion, so Ag plus, is produced once you get all of this in solution, right? This is going to be your oxidizing agent. All right, so Ag plus is going to be oxidizing this right over here, and that's going to produce a carboxylic acid, just like we would expect. This one has a really cool visual though, because as we know, the oxidizing agent itself gets reduced, right? So silver is going to be accepting electrons. So this gets reduced into just elemental silver, silver solid. And if you guys have ever seen silver, you know it has a very recognizable appearance, right? This is a named reaction. This is called the Tollens reaction. And one of the wet chemistry tests that you can do in the lab to detect the presence of an aldehyde is called a Tollens test. And you actually get a positive test by looking for production of this really neat little silver mirror deposit on some glass. I'm going to show you a video of this. That's why I've got the projector on. Just a couple of minutes, but pretty neat. So I wanted to show you. For you Zoomers out there, give me a second. See if this will work. Where's my YouTube? There it is. Okay. All right, so there we go. Sharing my screen. It's got a YouTube video up. Now I'm going to project. It says the video is like 6 minutes long. We're not going to watch the whole thing though. Volume's not very good. All right, let's try it now. Dude, what? I got too much crap going on that it's just like freezing. Ah. I promise the video is more interesting than this. Okay, it looks like we may not be getting audio. Sort of. But basically, let me tell you what's going on here. You see in those various graduated cylinders, you've got, in one of them, you've got a sample of something that's suspected to be an aldehyde. In fact, it's something that is an aldehyde. It's a sugar, type of sugar that is an aldehyde. And another one, you've got ammonium hydroxide. And in another one, you've got silver nitrate. What actually happens is once you mix the silver nitrate and the ammonium hydroxide together, it forms silver oxide. You don't actually just dump silver oxide in there. And then the silver oxide that's formed can act as your oxidizer. So I don't know which one is which, since they're all clear. So you can just watch the guy dump the stuff in the flask. This is a Florence flask, for those of you who have never used one before. Not a round bottom, it actually has a flat bottom. And so he's going to mix all of these clear liquids together. And eventually he's going to stopper it up. There you go. And he's going to start shaking it. And so what you want to do is you want to watch the walls and the sides of this. It's working perfectly on my computer. It's pausing on the projector for some reason. But if you watch this, you'll see a definite mirror effect start to develop in the Florence flask. It's going to become shinier. And so you can definitely, I think, see it already. Hopefully it'll stop shaking soon. You can get more of a still view. Let's see. Let's get fast forward to that part. Nope, there he goes. Yeah, isn't that cool? You can see his reflection very, very clearly in the flask. Yeah, his lab behind him and everything. Yeah, really neat. That is a positive test for presence of an aldehyde. Okay? You make the carboxylic acid. You don't really detect the carboxylic acid, but you can detect a byproduct here. Very, very nice little silver there. I had once had a student ask me, so if the whole class did Tollens tests and like test tubes, could I like gather up all the test tubes and like get the silver out and make, you know, some money? And I said, well, I guess you could. It's not very much silver though. It's very much a thin coating. So I don't think you could get very much money off of it. Plus it'd be a lot of trouble, but hey, you never know. Okay, so that's the Tollens reaction. Really cool oxidation. And that pretty much covers all the reactions in this chapter. I know there were quite a few of them, but you do see a lot of them had similar patterns that you could recognize. You kind of figured things out. All right, are there any questions so far? All right, let's try some synthesis problems now. And this is, you know, like I mentioned, this is going to be sort of another step up in synthesis. Mainly because of the organometallics, right? Previously, you learned if we wanted to add carbons, if we wanted to extend a carbon chain, we were pretty limited in our ways to do it, right? What was the main way that we learned to extend a carbon chain synthetically? Using a subtile ion, right? We learned that back in the alkynes chapter. Works very well. If you specifically want to put a carbon chain on a benzene ring, you can use the Friedel-Crafts reactions. This is going to be another good general all-purpose way of extending a carbon chain. Let me show you an example or two. Let's find some examples. I'm going to go straight to the back of the chapter for this. Okay, so let's try this. We're going to start off with a bit of alcohol. Excuse me. We're going to take 2 propanol, and we're going to try to convert it into right, this is pretty mild. This is a pretty mild synthesis. We can do this in technically 3 steps, although you might consider it as 2, technically 3. All right, again, take stock of what you're doing. All right, you're trying to extend the carbon chain. Right, we're trying to get an ethyl group onto your carbon chain. Could you do this with acetylide? You could, but it'd be a lot harder to do. It's a lot easier if you go the organometallics route, right? Any ideas? Going backwards or forwards? Think specifically organometallics. How could you use an organometallic to get an ethyl group on that carbon? 1,2,1,4 addition. That doesn't really add carbons to a chain. That, well, I guess you could actually. Yeah, never mind. Could you do it? Let me think for a second. Gray, I think there's something easier than having a 1,2,1,4 addition, because to have that, you'd have to have another double, like a carbon-carbon double bond. But I think I know what you're getting at. Are you thinking of something like this? Yeah. Yeah, that's just straight up reaction of an organometallic with a carbonyl compound, right? Ketone. So yeah, absolutely. If you had a ketone there, this ethyl group can attack. It attaches itself, makes a negative O, which then protonates. How would you get from the alcohol to the ketone? Oxidizing agent. Which one do you want to use? Any of them work.
PCC.
PCC is an excellent choice. Yeah. So get to your carbonyl compound. Once you have the carbonyl compound, then you can react it very, very well with an organic metallic. Okay. I could extend this a little bit too. Let's say instead of making this, my goal was to have made that. That's a little bit more intimidating looking, right? But actually, you could go ahead and convert it to this with just one more additional step here. It's an old one. How do you go from an alcohol to an alkene? Yeah, turn the OH into a leaving group. That's back in the alcohols chapter in organic 1. There's lots of ways you could do it. Probably the easiest thing is to add sulfuric acid. So yeah, I could have asked you to go from that initial alcohol to this alkene. Heck, I could have asked you to do this. I'm running out of space here. I could have asked you to go directly from there to there. How could we have gotten from the alkene to that? Again, an old reaction. Y'all remember? Addition to alkenes, chapter, I want to say chapter 10. What's that? Halogenation. Halogenation, BR2. So you see, there's a lot of different possibilities here, right? What you have to do is, again, if I asked you to go directly from here to here, that looks kind of impossible, but recognize the fact you need more carbons. That's the first thing, and you can see, you can fill in the pieces. And that's the thing. Again, looking at your exams and stuff, you guys, I think, are getting better with synthesis. You're getting more and more partial credit. But I want to just sort of alert you. Keep at it. Keep working out individual pieces at a time. Get them to add it. Let's try another. All right, let's see. You'll see a lot more of them worded like this. We're given a particular type of, functional group, in this case an alcohol, and it'll tell you like, 4 carbons or less or 3 carbons or less or something like that. and that has to be your only carbon source. And then so you look over here, and you're making what? Ketone that's got 8 carbons. So how would you go about this? Alcohols with less than or equal to 4 carbons as only carbon source to an 8 carbon ketone. What are some things that might enter your thought process here? What's that? NH2 minus the acetylide, using acetylide ion. You could do that. I'm going to make a caveat here because I want to get you guys thinking organometallics. We're going to purposely avoid the acetylide route here. We're going to see how to do this in organometallics. One good tip for a lot of these type of syntheses is to regard your product as basically a collection of individual fragments, right? You're going to have fragments that come together to make a larger product, right? Sometimes you'll have 2 fragments, sometimes you'll have 3, sometimes you'll have 4, whatever. How many fragments do you think you might want to try here in this example? As you go from an alcohol with less than or equal to 4 carbons to an 8 carbon unit. What might be the easiest thing to try? Well, you could try 8 1-carbon fragments. That sounds like fun, right? No? You could try 4 2-carbon fragments. What else could you try? 2 4-carbon fragments. That sounds a lot more acceptable to me, right? So that might be my strategy here, is to try to find a way we can get 2 4-carbon fragments together into one chain like this. Can anybody suggest a way that we could do that? And it may be a case where sometimes you figure out the middle part of a synthesis before you figure out either of the ends. That's something you run into more and more with these type of syntheses. In the interest of time, I'm just going to go ahead and sort of walk through this one. We're going to go over some more of these ones. All right, so one thing I'm thinking here is, well, I know I can get 2 4-carbon fragments together through an organometallics reaction, right? So what would happen if I had, let's say, and there's more than one way you can do this too, by the way. What would happen if we had, say, this? That 4-carbon aldehyde. And we reacted it with this, say a Grignard reagent. Tell me mechanistically, what's the mechanism? What would happen here? I left out a carbon, I think. There we go. What would attack what? You guys know this. Yeah, this carbon chain attacks this carbonyl, moves a pair of electrons up to oxygen, which grabs a proton. So it gives you this. And lo and behold, that's how we ended up getting our two fragments together, was through this organometallic reaction. Okay, does that make sense? And then you can just easily get from here to here by doing what? Oxidizing agent. We can add PCC again. All right, now we're not done though. We've got to show how we made each of these individual fragments from a 4 carbon or less alcohol, right? So it stands to reason that if this is our Grignard reagent, and this is where the magnesium was attached, that's probably where our alcohol was attached. So we probably started off with this alcohol. How do you make a Grignard reagent? Do y'all remember the basic ingredients? Look back. I think it's safe to say one of them is magnesium. So what do we have to add magnesium to? An alkyl halide. Do we have an alkyl halide? No. Guess what we got to do? We got to make it. So go back to last semester's reactions. Something like HBr. Give you that. And then you can add magnesium in the presence of diethyl ether to make your Grignard reagent. Boom. So that basically shows how you made one of your fragments. So this would be something that you would need to show. Okay? Does that make sense? Now you got to show how to make the other fragment. And it stands to reason the other fragment is this alcohol, excuse me, this aldehyde. So you probably started off with that alcohol. You can actually do this directly, except I added too many carbons. What will we need? PCC. Yeah. So these are a little bit different in how you approach them sometimes, because it's not necessarily just one big swooping curve like we kind of learned about. You kind of have to divide it into fragments, figure out how those fragments come together, and then figure out how you made the fragments in the first place. So these are a little bit more involved in some ways. Y'all understand how we did that, though, how the process for getting there. Like I said, we're going to do some more of these on Friday, so don't worry, we'll get more practice. Our quiz this week is going to be Friday. I didn't want to do it today. I'm not going to put synthesis on the quiz. Everything else in the chapter is fair game, though, all the reactions and stuff that we've gone over. Remember, Wednesday lab section does not meet today because of the ODK honors ceremony. Thursday section will meet tomorrow. All right. Have a good day. Rainy day.
Videos that you put up for the lab.
What's that?
Those videos that you put up for the lab.
Uh-huh.
Those for packing and future, like that contain all
Yeah.